Hi everyone, this is the NZQA scholarship exam for physics for 2022. Recently they changed the number of questions from 5 to 4, so there's more time that you can have for per question, and the time allowed is still 3 hours. As always, you still have a formula page if you need it, and let's get into the first question. Question 1, photons. Part A, the description of the photoelectric effect and the Bohr model of the atom both involve the concept of the quantization of energy. There are similarities and differences in how this concept is applied in these contexts. Describe one difference in the use of the concept of quantization energy between the photoelectric effect and the Bohr model of the atom. So this is just a matter of understanding of modern physics, which is an internal standard. There's a number of things you could say here, but you could just say in the photoelectric effect, photoelectric effect. It's the fact that the light is being quantized into photons. Or light energy. And it's being quantized as photons, and we know that the formula for that is equal to HF. And in the Bohr model of the atom, it's the energy levels in the atom which are being quantized. So the energy of the electrons in the atom. So energy of electrons being quantized. For this question, as long as you can say a specific difference between the two concepts, it's not really a matter of copying exactly what I wrote or what the marking schedule says. As long as you can justify your difference, it's okay. Okay, part B. A laser typically consists of a medium that emits light placed between two mirrors that form a cavity, as illustrated on the right. The cavity is similar to a closed box for the emitted light waves. The light-emitting medium can emit a continuous spectrum of light within a narrow range of wavelengths. The minimum wavelength of emitted light is 480 nanometers, and the maximum wavelength is 490 nanometers. The cavity is 5 centimeters long. Some wavelengths within this range are able to form standing waves within the cavity, and these are called standing wave modes. Calculate the number of standing wave modes possible in the cavity within the emitted 480 to 400 nanometer range. So this is a question that you may read and not know what to do initially, because they're not asking for like a specific physical quantity, like the velocity of this object or the time taken for something to happen. It's asking for the number of standing wave modes, which is something that you don't really see appear in any sort of equation, but we can sort of break this question down into just standing waves. So we know that it's closed on either side because there's a mirror on either side. So we can sort of imagine this light instead as like a string with both ends fixed. So the first standing wave, or the first harmonic, is this. And the wavelength for this is equal to 2L. Because you can imagine there's like a imaginary wavelength over here, which forms the complete wavelength from here to here. And so that is equal to double the length of the cavity. So lambda equals 2L. And this is for the first harmonic, so n equals 1. And then for the next case, you could have this. So then lambda equals L, and n equals 2. And in the next case, you have this. So lambda equals 2/3 of L, and n equals 3. So what am I trying to get with this? I'm trying to find just how the standing waves are being formed within a cavity of a specific length. So the length of this cavity that I've drawn here is L. And I'm trying to find each case where a standing wave can be formed. So you can find a standing wave formed for the first harmonic when the lambda is equal to exactly 2L. You could find a wavelength formed for the second harmonic when the wavelength is equal to exactly L, and vice versa. Oh, sorry, not vice versa, and so on. And so you can notice that there's sort of like a pattern for this. So first you start off with 2L, then you have L, then you have 2/3 of L. And if you're sort of following the pattern, you'll see that the next one should be 1/2 of L, and then the next one will be 2/5 of L. So what's the pattern? Each time, right, it's 2 divided by the harmonic. 2 divided by n. So if we look at this case, it's 2 divided by 1, which is equal to 1. For the second harmonic, it's 2 divided by 2, which is equal to 1. Oh, sorry, 2 divided by 1 is equal to 2. And then for the third harmonic, 2 divided by 3 is obviously equal to 2/3. And then for the fourth harmonic, 2 divided by 4 is equal to half, and so on. So the pattern that we have here is 2 divided by n is equal to let's see, 2 divided by n lambda is equal to, 2 divided by n L is equal to lambda. And so this is sort of a relationship that we can establish for any sort of standing wave, and we can just rearrange that like that. But how does it help us? N tells us the specific harmonic that we're dealing with. And if we know that, for example, n ranges from 1 to 4, then we know that 4 standing waves can be established, because we know that n can equal either 1, 2, 3, or 4. And so that's 4 standing waves in total. If instead we knew that n ranged from, let's say, 10 to 13, we still know 4 standing waves can be established, because we know that n can either be 10, 11, 12, or 13. And so those are all the possible harmonics for that range of n. So we can have 10th harmonic, 11th harmonic, and so on. In this case, we can figure out a range for n, because we know the range for lambda. They tell us the minimum is 480 and the maximum is 490. So if we can figure out the maximum range for lambda, if we know the maximum range for lambda, we can figure out the maximum range for n. And we know what L is. It's 5 centimeters. So it's quite straightforward. If we look at the maximum case, so if lambda is equal to 490 nanometers, then n is equal to 2L over lambda, which is equal to 2 times 0.05 meters divided by 490 times 10 to the negative 9. And that equals 2 times 0.05 divided by 490 times 10 to the negative 9. That equals 204,082. And because n has to be an integer, you can't have 1/2 harmonic. You would round to the nearest integer. And then let's say lambda was equal to 480 nanometers. Then n is equal to 2L over lambda again, and you just do a substitution again, and this time you do 480 times 10 to the negative 9. So what do we get now? 2 times 0.05 divided by 480 times 10 to the negative 9. 208,333. Again, to the nearest integer. So now we have a range for n. We can just figure out the difference between these two, and that tells us how many sort of n values that can exist within these bounds. So what's the difference? N equals 208,333 minus 204,082. So what do we get? 208,333 minus 204,082. We get 4251. And that's our answer. If the harmonics can only lie between the values of 208,333 and 204,082, then in total there must be 4,251 harmonics allowed within those two numbers. And so that's our answer. 4,251 total standing waves can be formed in this cavity within the wavelength range that they give us. So now we move on to part C of question 1. The process of nuclear fusion in the sun releases energy which spreads throughout space in the form of electromagnetic radiation. The photons that make up this radiation carry momentum as well as energy, with the momentum per photon given by P equals h over lambda, where h is Planck's constant and lambda is the photon wavelength. The sun loses 4.30 times 10 to the 9 kilos of mass each second due to nuclear reactions. Estimate the force exerted on the Earth by the photons it receives from the sun. Assume each photon has a wavelength of 550 nanometers, and that every photon that reaches Earth is absorbed. So again, at first glance, looking at this question, it is sort of very hard to understand what the path to solving it is. They've asked us to figure out the force exerted on the Earth, but we don't know too much other than the fact that the sun is emitting so and so amount of energy due to so and so amount of mass loss. But to sort of first have a little gauge of this question, they asked us to figure out the mass of the force exerted on Earth by the photons. And they've also given us the equation for the momentum of a photon. So immediately I'm thinking force and momentum, F equals delta P over F equals delta P over delta T, impulse. So that means we need to figure out just exactly how much momentum these photons carry. And for delta T here, we can also notice that they tell us something per second. Yeah, so loses that much of mass per second. So you can just assume delta T to be 1 second. So now we're concerned with simply delta P. What is delta P? Well, we know the momentum of a singular photon is given by this, right? But the sun doesn't emit one photon and that one photon hits the Earth. The sun emits a lot of photons and only some of those photons hit the Earth. So if we draw this out like a diagram, so we'd have the sun here and we have the Earth over here. Oh, actually, let me redraw this. We have the sun here, we have the Earth over here. The sun is emitting photons in all directions, right? But only some of them will reach the Earth. The issue is how many photons reach the Earth, and also how many photons are released. So to figure out how many photons are released in total by the sun, we know that the sun loses so-and-so amount of mass. And if we remember anything from our studies of nuclear physics, mass is equivalent to energy. And so this mass can be converted to energy, and so we know the sort of power output that the sun has. And at the same time, we also know that one photon has a wavelength of 550 nanometers. If we know the wavelength of a photon, we know its frequency. And we know the frequency of the photon, we know its energy. So then we know the energy of one singular photon from just the wavelength, and we also know the total energy emitted by the sun. Which means if we do a little bit of division, the total energy divided by the sun divided by the energy of a singular photon must be the number of photons that the sun emits. Great. That's the total number of photons that the sun emits, but how do we figure out the number of photons which actually arrives on Earth? Now it's just a matter of doing a bit of geometry. If we imagine that all the photons sort of spread apart in this spherical manner, and this sphere has a radius of r, and that same r is also the distance from the sun to the Earth, right? Then all these photons would hit the sphere, this imaginary sphere, and a certain fraction of them would hit the sphere exactly where the Earth is. So just how many photons hits the Earth relative to the rest of the sphere? Well, if we think about it like this, if we are at the sun and we're looking at the Earth, then technically all we see is a circle. At the same time, if we're at the sun and we look all around us at this imaginary sphere, again, we see a circle, the surface area of a sphere. At this point, some of you probably realized that to figure out the ratio of photons which arrives on Earth compared to the total number of photons, all we need to do is find the ratio of the surface area of the Earth facing us compared with the surface area of this imaginary sphere. Because that's how much of the imaginary sphere the Earth takes up. That's how much of the imaginary sphere the Earth can absorb photons from. So where do we get this data from? Well, at the beginning of the question, they actually gave this to us. So we know the surface area of the sphere, which helps us figure out the surface area of our imaginary sphere here. We also know the radius of the Earth, which helps us figure out the area of the Earth that is actually receiving those photons. And we also know the mean Earth-Sun distance, which is also this r here, the distance between the sun and the Earth, which is also the radius of this imaginary sphere. So, how do we do this mathematically? Okay, well, first thing is to figure out just how much energy the sun is losing. Now we're applying Einstein's famous equation, E equals mc squared, and we know that it loses 4.30 times 10 to the 9 kilos of mass every second. And we just do 3 times 10 to the 8 squared. And so 4.3 times 10 to the 9 times 3 times 10 to the 8 all squared gives us 3.87 times 10 to the 26 joules, and this is per second. So every second, the sun is releasing that much energy. And now, thinking back to what we were thinking about before, the energy of one photon, so actually let's label these so we know what we're talking about. So ET stands for E total. So energy of one photon is equal to HF, which we also know is equal to hc over lambda, just by c equals f lambda, the velocity of a photon. So we know that the energy of a singular photon is 6.63 times 10 to the negative 34 times 3 times 10 to the 8, all divided by the wavelength, which they told us was 550 times 10 to the negative 9. And so we get the energy of one singular photon to be 6.63 times 10 to the negative 34 times 3 times 10 to the 8, 550 times 10 to the negative 9. So then we get the energy of a singular photon to be 3.62 times 10 to the negative 19 joules. And now we just do a bit of division. So the number of photons, let's call this n, and let's also put a capital T there so we know it's the total number of photons, is 3.87 times 10 to the 26 divided by 3.62 times 10 to the negative 19. So 3.87 times 10 to the 26, 3.62 times 10 to the negative 19. We get 1.07 times 10 to the 45 photons. And remember, again, this is every second. Every second this is happening. So then, how many of those photons are arriving on Earth? Well, again, we're just taking the ratio of the Earth that is actually facing, the area of the Earth that is actually facing the sun versus that area of the imaginary sphere. Let's just call it sphere. So what's the area of the Earth that's facing the sun? Well, if we are the sun and we look at the Earth, then we simply see a circle. And that circle has a radius of 6.37 times 10 to the 6. And we know the area of a circle is just pi r squared. So it's pi and then 6.37 times 10 to the 6, 6.37 times 10 to the 6, all squared. And then the area of this imaginary sphere, well, we know that the surface area of a sphere is 4 pi r squared because they told it to us. And we know that the mean Earth-Sun distance is 1.5 times 10 to the 11. So we can figure out the surface area of this imaginary sphere by simply doing 4 pi times the radius, 1.50 times 10 to the 11, 1.50 times 10 to the 11, all squared. So what do we get? Pi times, and then 6.37 times 10 to the 6, all squared, and then 4 pi times 1.5 times 10 to the 11, all squared. We get 4.51 times 10 to the negative 10. So that means of all those photons that we calculated before, only 4.51, or only a proportion of 4.51 times 10 to the negative 10 actually arrive on Earth. So n on Earth is 1.07 times 10 to the 45 times this proportion that we just figured out, 4.51 times 10 to the negative 10, which is 1.07 times 10 to the 45 times 4.51 times 10 to the negative 10, 4.83 times 10 to the 35 photons. Remember, every second. Now, we can also figure out the momentum of one photon. Oh, I'm out of space here. I will just continue my work over here. So we also know the momentum of one photon, right? It's h over lambda. Again, we're trying to find the total amount of momentum that's actually hitting the Earth because of these photons. So it's 6.63 times 10 to the negative 34 divided by the wavelength. Again, we know that's 550 times 10 to the negative 9. So 6.63 times 10 to the negative 34 divided by 550 times 10 to the negative 9. So the momentum of a single photon is 1.21 times 10 to the negative 27. Again, kilogram meters per second. So what's the force? Well, we know that F equals delta P over delta T. I am actually run out of space. I'm just going to put it here. F equals delta P over delta T. And again, remember, all of these calculations that we had here occurred within 1 second. And so delta T is equal to 1. So we can just add 1 there. And then delta P, well, they tell us that every photon is absorbed, which means that the momentum of a photon changed from whatever it was before, 1.21 times 10 to the negative 27, to 0. And that's because once it's absorbed, it doesn't travel anymore, and so the momentum is 0. And so the change in momentum of the photon is simply just the momentum of the photon. So 1.21 times 10 to the negative 27. And we know there are 4.83 times 10 to the 35. So we just substitute that number in there because that's the total number of photons which are arriving on Earth. So now we just put that into our calculator. So that times 4.83 times 10 to the 35 divided by 1. We get a value of 4.82 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8 times 10 to the 8 newtons. And that's it. So part D of question 1, part I of D of question 1, comment on the significance of the size of the force exerted on the Earth by the photons. So this is one of those questions of physical reasoning, just to see whether or not you have like the common sense to see if these numbers that you get are correct. So we have a force of 5.82 times 10 to the 8 newtons as we just calculated, but is that significant when it's exerted on the Earth? There's a number of ways to think about this, but what I like to do is just, does this force actually have the necessary magnitude to affect something as massive as the Earth? So we are thinking about Newton's second law here, so F equals ma, but we are concerned with the acceleration. So if we have A equals F over m, is this force big enough compared to the mass of the Earth that the acceleration of the Earth would be significant, so that the Earth would start to accelerate away from the sun because of these photons arriving? So let's just see. What's the force? 5.82 times 10 to the 8. And what's the mass of the Earth? I believe they gave it up here. Yes, they do. 5.98 times 10 to the 24. 5.98 times 10 to the 24. So what do we get? 5.82 times 10 to the 8 divided by 5.98 times 10 to the 24. 9.7 times 10 to the negative 17 meters per second squared. This number is ridiculously small. The acceleration that the Earth is experiencing is very, very small. And so you can say acceleration. You can say negligible. Therefore, force insignificant. Obviously, in the exam, you want to lay out your wording a bit more detailed than I am, but for the sakes of this, you can understand it from here. So now we move on to part 2 of question 1D. If the Earth were covered by ice, it would be more reflective. Explain how this would affect your answer to part C. So if we look at part C, it was asking us to calculate the force exerted on Earth by the photons. If the Earth were covered by ice, it would be more reflective. So in part C, we said, or they told us to assume that every photon that reaches the Earth is absorbed. And so the final momentum of all these photons would then be 0, because if it's absorbed, then it drops, it just doesn't carry any momentum anymore, and the final momentum is 0. So mathematically, we can write it out like this. So change of momentum equals final momentum minus initial momentum. And because final momentum is 0, because the photons are being absorbed, this is just equal to negative pi, or negative initial momentum. But let's say the Earth were covered by ice and it was more reflective. Then the final momentum is no longer 0. We would actually get, so delta P equals PF minus PI. Because the final momentum is no longer 0, and because the momentum is, after the photon's being reflected, is actually in the opposite direction to when it came in. So obviously, the photon comes in like this, and it goes off like this. So PF is in the negative direction to PI. That means we have to apply a negative sign to PF, and leave PI as it is. And so what we notice about the difference between these two is that the magnitude of the second one is greater than the magnitude of the first one, because it has an added negative PF term. So what does this mean? If delta P, let's label this 1 and 2, delta P2 is greater than delta P1, we know that force is equal to delta P over delta T. The time frame that all this is happening in hasn't changed. We're still saying it's 1 second, as we said before. but delta P has increased because of the reflection, and so the force must also increase. Now, what's important to state, and what should help you get some like outstanding marks, is the force here is still insignificant. The momentum change of the photon can only be so great, and that would only cause the force to increase by small factors. Nothing too significant that would cause this force up here to become like orders of magnitude higher. And so what we can say is the acceleration would still be negligible, and so the force is still insignificant despite the fact that it increased.